All right, good evening, everyone, and welcome to our new round of YouTube videos for ECE Stats. Tonight we're going to look at Unit 3, Summarizing Bivariate Data. All right, so these videos have now been updated to include more of the more current things we do in the class, such as using the TI Inspire calculators and some of the spreadsheets that I have loaded on Google Classroom. So these have been kind of tweaked up a little bit. All right, folks, let's get right into it. So, in this particular case, we are looking at how the interaction between two variables can be categorized. So, in previous units, we looked at a single variable at a time. Maybe something like how heavy is your backpack, where we can find the mean, the standard deviation, or we can look at quiz scores and say, well, how did the class do in and of itself on this particular quiz? But what if I wanted to compare two pieces of information, say quiz 1 to quiz 2? Did students do better? Did students do worse? Is there a trend over time as far as scores go? Or is there a trend between really any two variables? So we can pick pretty much anything that we can try to find some sort of relationship between. For example, maybe we can, if I can, let me find a, there we go. Perfect, there's my pen. So let's say, can I find a relationship between, what can I find a relationship between? How about, I have my coffee sitting here with me. So is there a relationship between a number of cups of coffee and heart rate? So those are two things that we can measure, right? I'm not just going to say coffee. I'm going to say the number of cups of coffee because that's something that I can measure. Same thing with heart rate. Is there a relationship between coffee and your heart? Well, we may be interested in that, as a title for a study, but we have to know what we can measure. So we would say heart rate because, we can count, beats per minute, something like that. And my question throughout this whole unit is how strong is that relationship? And it turns out, for those of you that have studied line of best fit before, it's not as easy as just looking at one or two values. There is a lot of information that can help us decide what is a good fit and what is not. Okay, so here's one sample set of data that we collected in class. In this particular case, we have handspan and we have height. So this class is from probably a few years ago at this point, where I had everybody measure their hands from their tip of their thumb to the tip of their pinky, stretched out as much as possible. Usually people will measure their non-dominant hand doing this. For example, I'm a lefty, so I measured my right hand doing this. In any case, whichever hand was chosen, length in inches, and then height in inches of each person. So here we have a set of data. Now, the first thing that we could do is we could draw a scatter plot for this data, right? And we could try to assess visually what this data looks like. Remember that a scatter plot is basically a dot plot, but in two dimensions, right? We have both an X and a Y variable, and it allows us to see how the dots are in relationship to one another. So I could draw this out, but most of the time we're going to be using technology in order to do this, whether calculators or spreadsheets. So let's take a look at a set of data from this year that is directly from C block of fall 2024. Okay, so here's a set of data, and I have an X list and a Y list. So this is the spreadsheet, if you remember, that's located on Google Classroom. This is the 2024 variant of it, in case I update it further than this. Notice at the bottom we are on the two variable regressions tab. Um, so in this particular case, I have my X list, my Y list. These are all my hand lengths, and these are all my heights. Now, the rest of this we're going to get to later on in future lessons, but right now I'm more concerned about looking at the scatter plot. So here's my list. Over here is my scatter plot, X list versus Y list. Now, if I want to actually rename them, I can, and those names will change on here. So if I change this to hand, and if I change this to height, it should, I guess it doesn't update. Well, there you go. I tried. You could probably rename this if you really wanted to. But there's one thing that I do want to do in terms of chart editing. So one of the limitations of using this particular sheet in order to do these calculations is Google Sheets in particular has this odd quirk where it doesn't like to update the Y list, or sorry, the Y axis. It will automatically update the X axis. So if you notice, the X axis goes from like 6.5 all the way to 9.5 because that's the range of my X list. Now, Y list should do the same, but it turns out if you leave it to its own devices, it will automatically start the Y list at 0, or the Y axis. We don't always want that. So if you right click on the chart and you go to chart, I believe, if you go down to axis, vertical axis, you can change some of the characteristics of that axis. And here in particular, min and max, you can certainly either change these to numbers that befit the data that you have, or you can leave them blank. So again, here's what happens. If I leave them blank, you'll notice here that, again, it starts the axis at 0, and you have what appears to be a really flat trend. But there's a lot of wasted space on that graph. So I like to start the trend at a nice even number that's just below my data. That's why I chose 60, and my data goes as high as 75. So I would do axis, vertical axis, 60, 75. Now, you could do 62 since that appears to be the lowest number on here if you'd like, but that doesn't matter too much. What you're more concerned about is, can you see what the trend is doing? In this particular case, we can describe this trend. So how would you characterize the trend between the size of your hand and how tall you are? So if you think about it, we can imagine just from a basic understanding of biology that taller people have bigger hands. Or you could say that people with bigger hands tend to be taller because that's the way this data is going. We're saying we're starting with the bigger hands because maybe it's easier to measure a person's hand and say, well, if their handprint is bigger, then they might be a bigger person. This could have certainly use in forensics, say things like criminal investigations where you have a handprint and you measure it, and then from that you could determine potentially how tall a person is. Now, if you think about it that way, notice that you do have some wiggle room here. Look at some of these values. So, for example, all the people who have a hand size of 7.25, it looks like you've got a person around 63, 64, maybe 65, 66 inches tall. So hand size is 7.25 inches. That person might be 63 to 66 inches tall. If you come over here to larger hands like 9 inches, that person is 70 to 75 inches tall based on this data. So it certainly seems likely that, based on this data, that we could say that people with bigger hands tend to be taller. Now, the question we would have, though, is that a reliable trend? Like, would it be true for any two people that we pull from this data set? Or can you find cases that suggest the opposite trend? So, for example, if we look at, say, three people right here, if we look at this person here who has, let me see if I can find this in the chart. So it looks like it's at 64, 7.25. So that's this person right here. Let me highlight this one. We'll bold that. And then it looks like we have a person at 7.563. We'll bold that one. And it looks like we have another one here at 8.062. Bold that one too. So here's a case of three people where the hand gets bigger, but the person gets smaller. The person gets shorter. Well, that means that this trend isn't perfect. But for the most part, more likely than not, does it appear that the trend is in a positive direction? Certainly it does. So let's talk vocab. Now that we've had a chance to kind of analyze this, let's look at some vocab as it relates to how we discuss trend. So a positive relationship is what we call it when we have an increase in x that is paired with an increase in y. Think about this from Algebra 2, where if you have as x goes up, y goes up, or as y goes down, x goes down. So no matter which way you look at it, if they both go up together or both go down together, that's a positive relationship. And in a negative relationship, an increase in x is paired with a decrease in y. So, and vice versa. That means that they increase and decrease opposite one another. Now, we can usually tell that by looking at the graph, and we'll go back to that in a second, because we can kind of see how that positive and negative slope exists between the points. The one part that becomes a little bit more subjective is strong, moderate, weak trend. So we want to know how closely the data models some sort of discernible trend. Now, most of the time we're going to talk linear trend, but there are cases where we might think about a trend that is not linear, and we'll get into that as we go through. So let's go back to our graph. Let's see a little something here. So first off, would you characterize this as a positive trend or a negative trend? So now this graph does draw the line of best fit through here, which clearly shows that it is a positive trend. But even without that, we can tell that as x increases, we're generally seeing an increase in the y variable. Now, again, it's not going to be perfect every time, but we see that in a general case as we're going through. More often than not, the taller people are the ones with the bigger hands. Now, is this a strong trend, a moderate trend, or a weak trend? Well, here's kind of the difference. In a weak trend, what would happen is you would barely see the pattern. If at all, the data would look very puffy, where it's really hard to tell if the data is even increasing or decreasing. Because here we have data that is increasing, and that's pretty clear based on the points, it's at least a moderate trend. So with a moderate trend, you're going to see, in the most case, that trend appear. Here we see that positive trend, but you can definitely point out instances of groups of points that would follow an alternate trend. Like we did here, like we see this set of points that's forming an alternate trend. Well, that means that this is in the minority. The rest of the points are certainly following a positive trend. So I would call this moderate because based on the graph, we can certainly see several cases of the trend not being perfect. If the points were really, really close to a discernible trend, like it was very clearly a positive trend with the points deviating very little from it, then we would say that is a very strong trend. The problem, though, is one person's strong is another person's medium. And how do you tell the difference between weak and moderate and different levels of weak? And so we get to problems trying to figure out, well, what exactly is that characterization? And if you were to tell me, hey, I think that has a moderate trend, can I believe you? Or would you believe me? I would ask you, what proof do you have? Well, let's come up with that proof. That proof, if we go back to the notes, is going to be something called the correlation coefficient. And so what we're going to do is we're going to look at a numerical assessment of correlation. And this is Unit 3, Lesson 1, folks. Da, 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 da. Okay. So that numerical coefficient, first thing about it, don't try doing it by hand. It's tough to do by hand. So to actually calculate correlation by hand on this data set, I could do it for you, and I could do it by hand, but it's going to take me probably about an hour and a half to do by hand. No, I'm not going to do that, especially when this spreadsheet already gives you that number, and that is the value of R. This value here, make it nice and bold, boop, there we go. This value here is what they call correlation coefficient. And this is a numerical assessment of how strong a trend is. So let's talk a little bit about this number, what it represents, and why it's important. Okay. So one of the things we did in class as well, just kind of going back here, is we looked at several models here, just kind of thinking about what kind of trends that we have. So if you recall, we had strong versus moderate versus weak, right? So if we look at this first one, what could you tell me about this one? Maybe it's strong, positive. This is definitely a positive trend, and it's a very strong one because the points form really closely to a line. What about this one? Maybe moderate? Negative? Perhaps. Now again, the difference between, if you have a data set on the border between strong and moderate, could be a little of both, right? Because we can clearly see the negative trend. What about here? Here, there's really no trend. Is it positive? Is it negative? At this point, we really don't matter. So here we would say, weak to no trend. Or we might even say no discernible trend. Here's another way. So we could say no discernible trend. That's one way of writing it as well. What about this one? This data clearly doesn't form a line. Now I could attempt to make a line through the data, but I don't really want to because this data curves. And so I would draw a line that kind of sweeps up like that. Now, you might try to guess what kind of function that it is. You might think that it's a type of function that begins with e and ends with exponential. But maybe it's not. Maybe it's quadratic. Maybe it's cubic. Maybe it's a power function. Maybe it's logistic. We don't know until we test. So what I'm going to say for this is it's nonlinear. All I know right now is that it curves. Now, what curve it is, that's up to decide later. But for now, we'll leave it at strong linear. You could even have periodic trends. We probably won't do them much in this class, but you could have cases where the trend line goes up and down and up and down, and you may want to fit a periodic trend to see maybe how long does it take to repeat, something like that. Okay, so let's get right down to the actual values. So this thing that I talked about is called the Pearson correlation coefficient, and it's denoted by the variable R. And so in this class, from here on forth, I make a law, as I smack my gavel on the desk, that the letter R shall forevermore refer to correlation. Just like how n always represents sample size, x, the line over it, is always the mean, x is your data, s is always standard deviation, R is correlation, and shall forever be known as that. The gods have spoken. Anyway, this value can exist between -1 and +1. Think of it like a percentage, if you will, where it's telling you the strength of the correlation. 0.5 is 50% related. 75 is 75% related. The only thing that you'll see here is that it could also be negative. The value of R will tell you whether it senses a positive trend or a negative trend simply by having its sign. So if R is positive, right there's your positive trend, and if R is negative, there's your negative trend. So like here, you'll see here, weak negative, strong negative, weak positive, strong positive. And if the value is really close to 0, it means you've got a big puff cloud of data. The closer the data gets to 1, then the closer to a usually line, but the closer to your chosen regression model the data is. Because here we're going to focus on linear, we can say that for R, if you get a value of 1, it means the data is exactly collinear. The points sit exactly on the line. Guess how often that happens in real life? Yeah, it doesn't, unless you make it happen, right? Because data varies. That's the whole point. If you have a correlation of 100%, it means that there's no other variables that are causing variation. Then that's just silly. Okay, so here's a few calculator commands, and I'll show you how to do this on the TI Inspires as well in just a second. For those of you that are still operating on the old school TI 84s or 83s, for those of you still stuck in 1994, here's your directions. But again, we usually don't use this one again because we've upgraded calculators a little bit here. So one thing that I'll do is I'll show you how to find this in the calculator. So real quick, let's see if I can pull it up here. Where am I? There we go. All right, folks. Hey, look at this. I've got a calculator screen. Isn't this fancy? All right. So suppose you want to find values of R, right? Here's an easy way to do it. This one's got a few kind of interesting directions to it. There's two ways really to do this. We'll start with one way, but then we're going to might be doing it a different way once we get to the actual linear regression part. So anyway, let's go down to Add Lists and Spreadsheets, and let's create some data, right? Again, I'm not going to put a lot of data in here, but we'll call it hand, and we'll call it height. So we're going to put that in. Let's give it some values that we know. We can either pull some values directly from the table, or I can just kind of make them up as I go through. So just so that you see the correlation here, let's put it in and just make up some data. So 7.25, 8.5, let's do an 8, and let's do a 9. Okay, let's make up 4 points. And over here, let's get some heights on here. So let's say this person is 65 inches tall. This person is 71 inches tall. This person is 68 inches tall. and this person is, say, 70 inches tall. Okay. So we've put in some hands and some heights. Okay. Now suppose I want to find correlation. Here's what you do. We're going to come over here, and I'm trying to see where I should put my cursor. Let's just leave it here. I'm going to press menu. Okay. I'm going to go down, let's see, statistics. We could do stat calculations. Oops. Yes, we're going to go to stat calculations, and it'll ask you to do a few different things here. One variable stats, two variable stats. We're past those already. We're actually going to go into what's known as linear regression. Okay? There are two forms of linear regression. There's mx plus b, and there's a plus bx. We are going to use a plus bx. That is the one for this course, and we will use nothing else but that one. Okay. So once we go in here, we want to make sure that we put in all the correct equations. So notice here, these aren't quite right. So I'm going to make sure, essentially, your x list should be A and y list should be B, assuming you're starting from fresh list. So I'm going to do A, and I'm going to do control and parentheses, and that's going to put the brackets in. And we're going to do B, control, parentheses, puts the brackets in. So you should have x list of A, y list of B, okay? And I'm going to scroll down to the bottom, and all the way down here it says first result column C. Because what you want to do is you want to dump the results after your lists. Just hit OK, and here you go. All right. Now we're going to get to the A, B, R squared in a bit, but when I scroll down here, there's R right there, 0.907. Okay? All right. 0.907. All right. So there's a couple other ways that you can see this as well, but we'll get to that. So how would you characterize this trend? Well, let's go back to our notes and let's take a look here. So one of the things that we went back here, if we go back to right here, on this page, you're going to see in red a can statement. And so this can statement is really what we use to describe trend. From this point forward, we see a lot of statements like this where it's less about you synthesizing a response or you more just like fitting a response with the data that you have. So there is a strong positive trend between hand size and height. And there we go. And all you have to do is remove those and replace them with the appropriate context for whatever problem that you're doing, right? Okay. So let's go back to the calculator here. We have our value of R. And yes, it also tells you R squared. We'll more on that later. Now let's suppose you want to see the graph, right? If you want to see the graph, we're going to do much as we did before when doing dot plots. We press Control and Document, and it's going to add a page. I want to add data and stats. Ooh, okay. Points look like they're kind of all over the place. So add variable. I'm going to add, whoa, look at all of this here. Now this is interesting. You have a ton of lists to choose from. You didn't have that before. So the linear regression command calculates a lot of lists. That's actually really cool. And all of these are different variations on the data that we can analyze. So if we need some of these, we will. But let's go back to our original hand and height. So we had hand on the x-axis. Here's your dot plot. But I'm going to go over to the y-axis and add height. There we go. And here we have our scatter plot, where we can see that indeed taller people do have bigger hands. Now, this is only 4 data points, certainly, but you get a similar view as we did when we did this with our class data. So let's go back to the spreadsheet, and you can see here how we have a calculated value of R for all of our 22 data points. And we have a value of R of 0.795. So once again, there's a strong positive trend between hand and height. Okay, so next couple things that we could talk about is exactly the technical reason for R and what it's really measuring, and some other things that we can learn about it. So let's start with some important facts that you need to know about R. First off, the value of R does not depend on the unit of measurement. What if I measured you in centimeters? What if I measured you in potatoes or washing machines? Would you still be correlated? Yes. You would still find that bigger people have bigger hands, regardless of how we measured it. So the value of R does not change for units. And that's because R, if I can write this down here. Oops. There we go. Perfect. R is a unitless measure. That means that it's not going to change depending on units of measure. Same thing with X and Y, right? Now, if X is related to Y, would it be true that Y is related to X? Sure, right? If bigger people tend to be, let's see, bigger people are taller. Yes, okay. If bigger people have bigger hands, right? Then would people with bigger hands be taller? Yes, that relationship works both ways. So the value of R does not change when you look at an axis versus X versus Y. And we can show that on the calculator by actually exchanging these. So here's the relationship of these points, right? Kind of form a line. If I take this and make that height and that hand, look what happens. It literally just reorients the data into a different direction. It takes basically the graph and flips it around. That's not going to change where the points are in relationship to one another. So if there was a trend before, there's still a trend here. So these do not change R at all. Now, another thing is just here to keep in mind. A value of R close to 0 does not rule out a relationship. You just haven't found it yet. Maybe it's another variable. Maybe it's a nonlinear relationship that we don't know. Maybe it's a different kind of function that we haven't studied. So a value of R close to 0, but we still think there's a relationship, we just have to explore it further. Okay, now the next question might be, how do we actually calculate this, right? Now, obviously, we have the spreadsheet. But just in case you're curious, here's what's happening. In order to find R, what you first have to do with your list is you have to calculate the mean. If you have your X and Y list, right? Here's X, here's Y. Data. The first thing that you have to do is you have to find X mean and the standard deviation for X, the mean of Y, and the standard deviation of Y. You have to start by finding those. And as you know, just doing this by hand is tough anyway. Then what you have to do is for each data point, you have to find a z-score. And so you have to basically convert each and every data point into data minus mean over standard deviation, and you do that for both the X and the Y. And you do that for every single data point. Once you've got all that done, you then multiply the x and the y pairs together, add it all up, and divide by n minus 1. Sounds like a lot of work, right? That's why we use a spreadsheet. But what does that mean? What that means is what this formula is doing is it's looking to see if values that are low match with values that are low. So in other words, if we had, say, a point that is one standard deviation below average, does it pair up with a point that is also one standard deviation below average? If you had a point that is about average for x, if it has an average x, would that average x point have an average y point? Or would you have a case where you have a point that's, say, a high-end outlier for x, but is only slightly above average for y? If that's true, then we don't see a very strong trend. That's what this formula does for us, is it's looking to quantify how close the z-scores are to one another. Now, there's a more direct version of calculating this, which is down here, but it still involves finding the sum of x, the sum of all the y's, the sum of the squares of all the data, and just ick, right? So guess what, guys? This is nice to know as far as the technical part, because correlation is based off the fact that similar z-scores will be paired with one another. But beyond that, I'm never going to make you do this by hand. Let's be realistic. When you leave college, when you leave high school, whatever it is, you're going to have calculators. Google will be your best friend. So anyway, that's really what R represents. And like we said before, we'll skip that for a second. I had another page here. I think I accidentally deleted it. Okay. Essentially, here's what I said. If the points are in the same relative location to each other for y as they are for x, then we have a trend. If the z-scores are not the same for y as they are for x, then a trend isn't present. Once again here, you won't see this that often, but we're usually for R, it's a sample correlation coefficient because we take a sample of data. But this Greek letter, which is actually the Greek letter rho, and is the R-sounding Greek, that's the population correlation coefficient. If we knew the correlation for the entire population, we would use that. We're really not going to work with that in this class. Just it's there as a completeness sake, because don't forget, we do that for mean. We use either x with a line over it or mu. For standard deviation, we'll use S or we'll use sigma, depending on whether we're dealing with the sample or we're dealing with the population. Okay, and other than that, though, really, your biggest things here are just making sure you understand where to find R and how to measure it properly. So the last thing I'm going to leave you with is an interesting website you can take a look at here down here if you're kind of curious. And some final things that I want to point about this unit. Folks, we are not at the moment doing experiments with this. We're simply looking at data. And just because we see a correlation does not mean that X is causing Y or Y is causing X. So big hands do not cause people to be tall. Being tall does not cause people to have big hands. They just happen to have a relationship. Now, is there something else that's causing those to happen? Sure, biology, right? But, those two don't simply cause each other. Here's a great example of that. Many studies have shown that consumption of hot chocolate is negatively correlated with crime rates. That means that as people consume hot chocolate, crime rate goes down. And studies show that. There is a strong correlation. But Why? Does hot chocolate cause lower crime rates? No. I mean, gives us the warm fuzzies, and I probably want to less commit armed robbery if I'm full of delicious hot chocolate, but no, wait, no. That doesn't make sense. So why is this true? Consumption of hot chocolate. Where do we consume hot chocolate? In cold, right? More hot chocolate is in colder climates. Now, also in those colder climates, there tends to be less crime. And for several reasons, mostly because with the elements kind of against you, um, more people are looking for ways to simply survive the cold rather than committing crimes. Now, granted, one of the things about committing crimes is people do commit them as a means of survival. So, you might get the odd case where somebody maybe steals something to keep themselves warm. Sure. But most of the time, um, people who are more prone to commit crimes during the winter, they're going to be focused on staying indoors and staying warm. They tend, again, loose correlation here. I'm not stereotyping at all, but people who commit crimes are more likely to worry about finding places to be where they can keep warm. They may not have all of their needs met, which is why sometimes they turn to crime. So those are people who tend to need to focus on surviving the elements like that. So there's not likely to be as much crime. Okay, so again, correlation is not equal to causation. And with that, I think we're about done here. Go ahead and work on the lesson one problems for Unit 3. It's mostly about making statements and just understanding the purpose of R. Um, there you go. Have yourself a lovely evening, folks, and we'll chat again soon.